Yeah, thanks, Rory. Thank you, Dan. And thank you, Sophia, for doing all of the heavy lifting on the manifold stuff. I'm talking about manifolds too in a slightly different, maybe less physically geometric context, but essentially using manifolds to look at and help us understand the development of the brain's visual system. And we're going to use a theory from manifold geometry to help us understand that. So this is kind of a general paradigm for how we look at vision in computational neuroscience, where the goal is essentially to get a model to do the same kinds of tasks and computations that the brain does. So the benefit of this approach is that we can probe models in ways that we can't yet do to the brain, allowing us to use frameworks that can help us mathematically formalize complex brain functions into tractable tasks, which I'm sure many of you who do computational neuroscience can appreciate. So some examples of this, so essentially what you want to train your models to do is map some input data into the model and then get the model to do some kind of tasks based on the input data. So the most common example, I think, is image classification. So if you have images of cats and dogs, you want your model to be able to recognize one from the other. You can try to find a representation of this data that looks somewhat like the brain's representation of this data. This is what sparse representation might be trying to do. Maybe frame prediction too, predict the next frame in a sequence of frames. It is something that the brain also does and that people have devised models to do. And today I'm going to be talking specifically about object recognition and how we can model this. So the way we formalize object recognition using manifold geometry is you can think of the data set of images of dogs as occupying a set of points in a high dimensional space. And we're going to call this like the dog manifold. So every time you look upon a dog, you plot a point basically that traces out this manifold. And then the cat manifold is a separate manifold, but in terms of the actual pixel representation, or maybe you can think of it as the representation on your retina, these manifolds might be quite tangled and difficult to discriminate between one or the other if you were just trying to classify these manifolds as is. And so what manifold geometry says for neuroscience is that as information gets transmitted through the visual system, the firing patterns of the neurons that encode the data in such a way that firing patterns of neurons encode the data in such a way that it untangles these manifolds as you go down the visual stream. And by the time you get to the inferotemporal cortex, where people suppose that object classification or object recognition actually occurs, these manifolds are very separable. So if you're familiar with statistical learning and you use like perceptrons, this is just trying to stick a hyperplane between your data classes. The difference here is that we're not looking at points as the counting unit. We're looking at trying to classify actual full manifolds. So the reason this framework is so powerful is because there's actually theories that have been developed to quantify how separable these manifolds are, in the same way that theories have been very well developed for the perceptron for many years. This measure I'm referring to here is called capacity, which essentially measures the number of manifolds you can separate into distinct object categories, and capacity is a function of the actual geometry of the manifold, of the data manifolds you're considering. So intuitively, capacity, what it's saying is that the higher the capacity, the easier it is to discriminate between different object categories. You can also think of this as how many categories you can actually store given the constraints of your network, like how many neurons are in your network. Or you can also think of it as like the per neuron information content that you can actually, like looking at each individual neuron, like how many categories can it store? So a caveat of this work is that this paper specifically here, Cohen et al. 2020, looks at a network that's already been fully trained using labeled images and gradient descent. Any of you have run an image classification probably know. But if we really want to understand how the brain learns the synapses and connections to do this, we adopt the perspective that, okay, so somehow evolution successfully produced the visual system that we're trying to emulate. So we must be able to arrive at a model that can do the same exact thing as these neural networks, but that's governed purely by biological rules and constraints and is implementable by neurons. So we're not just recreating the visual system at a functional level, but actually understanding how computationally the visual system develops and how we essentially learn to see. And this amounts to rethinking how we train these models. Oh yeah, and this is just, visual to illustrate what capacity is doing. Just makes it easier to discriminate over time. So yeah, how does the brain actually learn to recognize objects? And to do this, we can inspect what actually happens in the development of the mammalian visual system. So here's a set of functions that emerges during development. And it turns out for the really core functions, which are on the left, you don't actually need vision at all. A lot of the core visual circuitry that does the functions that we're familiar with, like orientation selectivity and direction selectivity, emerge without the need for visual experience. And we know this because by the time a mammal's eyes open, like during development, these properties are already well formed in the visual system. And retinotopy is actually the formation of synapses from the retina to higher visual areas. So this all happens before light even hits the retina. So surprisingly, the brain doesn't even need a visual experience for the most part. A lot of it is just maintenance, as you can see on the right. And so you don't need a stream of visual input for these core visual circuits to form. In other words, you don't need this like labeled training data. I mean, maybe the brain probably doesn't do like actual labeled data at all, but essentially you don't need like the stream of visual input. So how does vision actually develop without a visual experience? Well, there's a couple factors that can account for this. One of them is specified by molecular signaling, and the other is in terms of spontaneous activity. And one factor is a phenomenon called retinal waves. So this is a pretty beautiful phenomenon, I think. So early on in development, while the eyes are still closed, before light even hits the retina, this waves of propagating activity come across the retina in this like wave-like pattern. And this happens, they look like wave fronts or circles. You can actually look at this. This is calcium imaging in a mouse that's at postnatal day 9. So this is a small portion of the retina, but you can still see the waves, and it's sped up like about 10 times. So this is data that's been collected at Berkeley by the Feller lab. Marla Feller is an expert in these. And it turns out if you eliminate these retinal waves, you don't form the mature connections to higher visual areas. So we think that retinal waves are some kind of training signal that teach the brain how to do these visual functions. But how can we actually model this? So what I'm proposing is that we can have two training phases when we train our models. One which captures what happens in this experience-independent part, where retinal waves are being shown, or retinal waves are occurring, but no visual experience is occurring. And then one which affects a post-visual experience, during the visual experience, while you're actually attending to visual input. So the model architecture that I'm using, I'm not the first person to have this idea. So there's this model that's been developed by Raghavan and Thompson. Essentially, it's a very simple model. It's a 4-layer, you can think of it as a neural network. The input layer is analogous to the retina. So the data that you show the model is projected onto this input layer. There's 2 fully connected linear hidden layers. And then finally, there's an output, which is just SVM classifier. And you can think of this as the thing in the network that actually does the object discrimination. And so how do we actually train this? Well, there's a pre-training phase where it's completely experience independent, that's completely reliant on these retinal wave patterns. And here I'm showing on the left, there's actual retinal wave data and model retinal wave data that was used in this original paper that's a bit more tailored for the task. I can explain more about how they differ later. But essentially what's happening is, so for all the blurred parts, no training is going on. It's just Hebbian learning on the first layer of the network and using a winner-take-all mechanism to form the connections from the retina to, maybe you can think of this as like the LGN, or the first visual area after the retina. So you just do this very simple learning rule to learn the weights connecting these 2 areas. And then after this, you feed actual data that you want to classify. So this is just MNIST data, so handwritten digits from 0 to 9, but they're projected onto this retinal input space. And you pass the data through the model, and then you only train that last support vector machine layer on this, on the data, but you freeze the weights of the rest of the model. So you're still getting the representations that you gained from doing retinal wave training. And then the task that you're doing is, again, image classification. So we basically want to compare what happens when you don't train with retinal waves, or when you train with retinal waves at all, and what retinal waves are actually doing to this internal representation to make object discrimination maybe easier or harder? What is it actually doing with regards to the task that we're interested in? And to just show you that we're actually doing something when we train these retinal waves, we can look at the receptive fields of these models before and after this pre-training in the experience independent phase. So the pre-training with simulated waves essentially gives you receptive fields that mirror the retinal wave data. And then we also have pre-training with real waves, which actually look a lot more wave-like. And then this is the randomly initialized model before any pre-training on the right. And so what happens when you do this and you actually run classification? Well, it turns out that pre-training with receptive fields actually improves your classification accuracy in the final layer. So you can think of this as happening is, well, so the first on the left is just the pre-trained simulated wave network. And then the third set of bars is the pre-trained real wave network. And then the two lower bars are, you take those same receptive fields from those networks and create a new network where you just shuffle the pixels of all the receptive fields in the pre-trained networks. And the idea is just to get receptive fields with the same exact statistics, but destroy all the spatial structure, which we think retinal waves are actually like doing to instruct the brain. And you can see that classification accuracy is better for those networks that actually have some sense of spatial structure built into them from the pre-training. So the idea is that, okay, well, maybe retinal waves can help you achieve internal representations that are more separable. So the idea here is that if we can draw a plane between these two object manifolds, this is equivalent to separating them, as mentioned before. And then networks that are pre-trained with these retinal waves are actually better at doing this. And then once again, we can look at this capacity measure to tell us exactly what, like how separable these manifolds become once you pre-train with these retinal waves. And it pretty much follows as you'd expect. So once again, capacity is how easy or hard it is to discriminate these real life objects. And capacity is just a function of each manifold's geometrical properties again. So you can see that from the input data or the input layer to the first layer of the network, the manifold capacity actually increases. And this is something that's been replicated in other artificial neural networks like AlexNet or BGG, like things that do these like very large classification problems, like much larger than this, where you actually see the manifold capacity like increase layer by layer. And it's really a statement about the representation at each layer and what each layer is doing to the manifold geometry of the original data. And then the last bar, we have the scrambled data set where it's just the retinal wave pixels shuffled again. And you can see the manifold geometry just isn't as favorable for classification. So this is preliminary work. There's lots to be done. So one thing that we really want to do is collect more retinal wave data. We're fairly data limited. I don't collect the data myself, but what I was showing you is a very small portion of the retina. What we want to be able to do is like actually look at what's going on in the entire retina and see what sort of spatial structures are training essentially the connections to LGN and superior colliculus. We want to look at more naturalistic tasks. So MNIST classification, it's not a very natural data set. So you can actually try to classify maybe natural images. And one thing you can observe from these results is that the real waves actually perform slightly worse relative to the simulated waves. My thinking here is that the simulated waves are a lot more localized, if you remember what the receptive fields look like. And it seems to be a lot more tailored for this like MNIST task where these individual points can tell you a lot about what the MNIST data set looks like. These real waves are a lot noisier and resemble curves and edges that you might find in a natural image data set. And they're obviously just more noisy because it's real data. But what I suspect is that these like localized receptive fields won't be as good at separating the manifolds of real data because they don't contain like all this other spatial information. Again, that was a very simple model of retinal waves. You could certainly use more complex ones. And then finally, we want to use more complex models and learning rules. So in terms of models, there's actually, so we're only looking at really this first layer from the retina to the LGN. What we want to do is extrapolate to higher brain areas, like V1, because realistically, object discrimination doesn't happen probably until the inferotemporal cortex. So there's four visual areas roughly. So we want to see how the representation changes by applying receptive fields of those visual areas to these transformations, and then also varying the learning rules. We use a very simple Hebbian learning rule, but in reality, the circuit that forms after retinal waves occur in the retina actually is like a feedback circuit. There's lots of nuances there, waves induced in higher visual areas that aren't retinal wave-like. Like there's waves induced in V1, for instance, that probably have a lot of complexity that we're not accounting for. And we also, again, retinal waves are a spatiotemporal phenomenon. They have a time component and there's time correlations in that data. We are using a model that is only learning classification on a problem where there's no time component. It's just MNIST. So ideally, we could find a task, something more like frame prediction, or something where you learn direction selectivity or something that involves motion. I think would be really cool, and certainly a goal of ours. And so really what the take-home message of these talk is that, so solving vision, at least from a biological standpoint, requires solving what happens before vision, before the visual experience actually occurs, if we want to be faithful to biology and we care about modeling the brain. The other thing is that model training can be adapted to reflect these biological realities and become more biologically plausible. Again, adopting the perspective that nature did it, so there must be some model out there that captures what nature does. And then finally, training with retinal waves leads to these favorable representation geometries as the data is transmitted throughout the visual stream. And varying how these retinal wave patterns are and varying the learning rules probably have implications for what it does to the data manifold geometry. So that's all my time. Thank you to Suyang Chung, who was really foundational in the work of looking at these data point clouds as manifolds and developing theories from statistical mechanics. And I didn't show any of the math, but there's a lot of math that goes into just like creating those simple little bars that are all basically from statistical physics, which is amazing. And Maya Pitcher, who collected the data at Berkeley, she's a PhD neuroscience student. And Marla Feller, whose lab Maya is a part of, she did a lot of the foundational work on uncovering what retinal waves do, and yeah, so I'm very grateful to them and my funding. So thank you for listening.